Hello, hello. As you're getting settled, let me know in the chat where you're calling from and what experience you have with the GRE, if you have any. And I'm pretty sure I set up the chat that it should work, but if it's not working, let me know in the Q&A, please. Great, we've got Jessica from Queens coming in with no experience. That's great, I'm glad you're here, Jessica. Amy's here from Raleigh, North Carolina. Great, glad the chat is working. Amy also coming in, no experience. That's fantastic. That's what we're here for. Other folks, where are you coming in from? Great. Shella is coming in from Brooklyn, also no experience. And Laura from Los Angeles, thinking about switching from the GMAT to the GRE. Great. I personally like the GRE a lot more. I think the GMAT is a much more punishing test. And this will be helpful for you, Laura, because we're going to focus on a question type that's only on the GRE today. So hi, I'm Jerry. I'm going to be your teacher tonight. And what I want to focus on is a particular technique that we can use on a particular kind of question on the test. The questions are called QC questions, or quantitative comparison. So we'll start off by just going over how this format works. There are other videos that get more into sort of the basics of the format. This is going to be looking at one particular way to approach them. And so I just want to remind you all, I'm really glad you're all here, and I'm glad there's so many of you that you're like, I'm just starting. That's fantastic. This is a great place to start. And if you like what happens tonight, check out the archive of these. This is being recorded, and the archive of these will appear on YouTube. So if you go on YouTube, you look up Manhattan Prep Free Prep Hour, there's tons and tons of these about just about any topic that you might want to review. So what we're covering today is how to use algebra in these QC questions, the specific technique we'll call the hidden inequality. So just to sort of get us into here, a quant section has got 20 problems in it, and you get 35 minutes. And those problems are all mixed up in terms of what they're about and how difficult they are. But the one thing that is predictable is the format of the question. So the first batch of questions you get are going to be quantitative comparison questions. That's what we're focusing on today. There's then discrete quant, which is like your standard multiple choice stuff, data interpretation, where they give you a graph and ask you about it, and then more standard multiple choice stuff. So for today, we're just going to focus on this first batch of questions called quantitative comparison. And in a very basic form, this is what they look like. You sometimes have what we'll call upfront info. And this could be anything from a definition of what X is to a whole word problem or geometry figures or anything else. Or there might be nothing there. In every case, the question is always the same. We've got these two quantities, and your job is to compare them. And so it's worth knowing the choices that we pick the bigger value, we pick C if they're equal, and D if it can't be determined. We'll talk a little bit about what that means in a second. So in a second, we're going to try one. And from that, I'm just going to kind of build out some of the foundational strategy that then we're going to move into this particular technique today. But before we try that, I want to just give you the advice that I give all of my students of how to begin a problem. Any problem, quant or verbal. Start with 3 things. PDA, like what you're not supposed to do in high school. Put your pencil down, take a deep breath, and to actually read the question. It's worth taking your time at the beginning to see what's going on with the question before you start to solve it. The biggest mistake I often see is people start solving before they've even assessed what's going on. That means you're likely to waste time, you're likely to make mistakes, you're likely to miss important information. So try to start with PDA. And then for this next problem and all the ones we do, I want you to think about how you organize your page. So if our problem looks like this, on your page, you basically want to copy it down. Give yourself clear column A, a clear column B, copy the upfront info insofar as that's helpful. And then know your choices, and you may be helpful to have this written down on your page, though I'll have it on the slides as well. And then we can work out the math, keeping good records and staying neat. And if we see, okay, this side is bigger, that means the answer is B. So I just want to emphasize, keeping clear and steady records of your work as you go is a really important technique, just to make sure you don't make the kinds of careless errors that on this test can count just as much as not knowing how to do something. Okay, so we're going to try a fairly fundamental question. Doesn't mean it's easy, but just fundamental in that they get more complicated. And from that, we're going to talk about the overall aim on a QC problem. And from there, we're going to start moving into this new technique. So start with a deep breath. And send me your answer in the chat when you have it, please. Okay, so looking at this problem, we might first approach it, especially if we don't have any experience and don't really know how the test is trying to trick us. We might look at this and say, all right, x equals 2y. So that means I need 2 y's for every 1 x, which means the y's are smaller, and the answer is A. But that's not right. And this is the first tip I'm going to give you, is don't trust simple appearances. If something looks super clear, where you don't have to do any kind of calculation, you don't have to investigate it in any way, it's too easy. If you had to do something and then you easily solved it, that's a different story. But here, where you're just looking at it and you're like, I think x is bigger, chances are there's a trap. And let's look at what that trap is. So if x equals 2, Well, then x would equal 2 and y would equal 1. And a is bigger. But what if x were -2? Then we get -2 and -1. And in this case, y is bigger. As soon as you have two different relationships, the answer is D. And this is what we mean by this relationship cannot be determined. Really, it means it depends. So this tells us what our job is on QC. When I see a QC problem, I want to first try to simplify it any way that I can. And we'll see a lot of problems today where simplification becomes really important. And then after that, I want to do what I did here, which is not just trust the appearances, but I want to pick numbers and try to prove D. My goal is to get two different relationships. In terms of what numbers to pick, a helpful tool is the mnemonic Zone F. 0, 1, negative, extreme, which just means change the scale. Get bigger, get smaller, and fractions. If you're trying to think about what to plug in, try using this as a technique. And for instance, on this problem here, if we had chosen, say, x equals 0, that would have given us, oops. If we had chosen x equals 0, that would have made both quantity A and quantity B 0, which also would have proven D for us. So all we need is any two of these, and that tells us the answer is actually D. I know this is a lot of information that's coming at you relatively quickly. I want to pause for a second and take any questions because we're going to build from here. Okay, so for QC, good question. So Jessica's asking, why would it be D and not C with 0? So you're right. If I'd only plugged in 0, it's giving me C. But the fact is, I'm getting different answer choices. As soon as I get two different answer choices, whether that's A and B or B and C or A and C, whatever, as soon as I get two different ones, then I know the answer is actually D. Good question. So I want you to keep this idea in mind as we do our work today. And as I mentioned before, we're going to focus on ways to simplify problems. But keep in mind that in all the problems we do, after we're done with simplification, if that doesn't solve it for us, we're then going to try to pick numbers and try to prove D using Zone F. So this technique is simple enough on a problem like this that's pretty clearly set up. But what if we saw something like this? Really complicated. And I could plug in numbers to try to prove D, but it's going to take a while because for any number I plug in, I have to plug it into all of these different places. For me, that's where I make mistakes. If I'm doing a lot of arithmetic, I'm going to mess up somewhere. And it's hard to see what numbers would I need to plug in to make this do something interesting. But I might also notice, like, wait a second, I've got 12a squared, 12a squared. Like, these things look similar. What we're going to ask is, can I use the similarity between the two sides as a way to make this problem a little simpler? We're going to come back to this in a second. First, I want to look at a much, much simpler problem. Quantity A, 10, quantity B, 6. How nice. It's quite clear the answer here is A. But I want to try something. What if I added 5 to both sides? Well, my numbers are going to change, but the relationship doesn't. The answer is still A. And on a QC problem, I don't actually care what the numbers are. All I care about is the relationship. So if I add 5 to both sides, I didn't change the answer. If I subtract 10 from both sides, the numbers change, but the answer doesn't. If I multiply, the numbers change, but the answer doesn't. Divide, the numbers change, but the answer doesn't. And this is the foundation for the technique we're going to work on today. That basically, when I see a QC problem, I can treat it like it's a big inequality. Because ultimately, that's what it is, right? It's 10 is greater than 6. And the question on a QC problem is, what's the inequality sign? Is it greater? Is it less than? Is it equal? Can it change? So just in the same way that if I had, 2x plus 5 is less than 7, I could subtract 5 from both sides and then divide both sides by 2 to solve for x. In that same way, I can do that with the sides of a QC problem. There's one major exception here, which is if I multiply or divide by a negative number, the sign is going to flip because I'm dealing with an inequality. And this is a rule from inequalities. If I've got negative 2x plus 5 is less than 7, and I subtract 5 from both sides, and I divide both sides by negative 2, the sign is going to flip. This is true of any inequality. So, because our job on these questions is to figure out what's the inequality sign, I want to avoid any move that might mess that up. So I'm not going to multiply or divide by negative numbers because I don't want to mess up my answer. Questions so far? We're going to practice this a lot today. So if this is feeling a little bit hazy, it'll get clearer. So when I see algebraic expressions in the columns of my QC problem, I'm going to use this hidden inequality trick to simplify across the columns and then do what we always do on QC, pick numbers and try to prove D. So let's return to this ugly problem we started with. I see I've got 12a squared on both sides. So I'm going to start by subtracting 12a squared from both sides. That already gives me something much nicer to work with. And at this point, I have a choice. Do I want to simplify more or pick numbers? It's up to you. You might say, this is easy enough, let me start plugging in. Or if you want to simplify more, you can essentially solve for a variable. In other words, isolate it. So let's do that. I'm going to add 19 to both sides. So now I've got 10a versus 4a plus 10. I could pick numbers here, or I could keep going. I'm going to keep going. So I'm going to subtract 4a and get 6a versus 10. I could plug in here or I could keep going. I want to keep going. Personally, I find it easier to do algebra than to plug stuff in. So I'm going to divide both sides by 6 and get A versus 5/3. And now, at this point, this is the place where students often become a little confused when you're doing this for the first time. At this point, or at any point, we now are going to do what we always do. Pick numbers, try to prove D. And the point of doing all of this algebra was that now that last step is super easy. So I'm going to say A equals 1, which would be less than 5/3, or A equals 10, which is greater than 5/3. And I've proven the answer is D. So I went from a problem where it was very difficult to plug in numbers to a problem where it was so easy to plug in numbers I barely have to break a sweat. As an individual test taker, it's up to you how much of this you want to do. If you're like me and you find algebra easier than arithmetic, by that I mean I can do this without much difficulty and I'm less likely to make mistakes doing this than I am trying to plug in up here, you might want to go all the way down to isolating the variable. Or if you prefer to plug in, you may want to start plugging in earlier. Maybe you get rid of the a² and plug in here. It doesn't really matter. What I want you to be aware of is the choice that you have to simplify. And on the problems we do today, simplification is going to be your friend. So I'm going to give you the first problem for you to try this. And I want you to think about, how can I do math across the hidden inequality to simplify the problem before I try to plug in or solve? Send me your answer when you have it, please. Okay. So for this problem, you might notice I've got 3 to the 5th and 3 to the 5th. So I'm going to try to do something about that. I'm going to set up my hidden inequality. Often it's helpful to like draw a box or draw a question mark between them. I used to do an equal sign and then I got confused and thought they were always equal. So I like a question mark or a box. And then I'm going to add 3 to the 5th to both sides. Now, this looks a lot better. And I could just put in my calculator 3 times 3 times 3 and 9 times 9, or maybe I know these and I can see that b is greater. Now, of course, could I have done that from the start? Sure. But it's worth it to do the little bit you can to make this part a little bit easier. Let's try another one. Okay, so this one looks a little more complicated than the other. We might be thinking I need to use a lot of exponent rules or something. I cover that in another video, but you don't actually, because let's notice, all right, 3 to the 20, 3 to the 20. Great, let me try to simplify this first by dividing both sides by 3 to the 20. So I end up with 2 to the 20 versus 2 to the 15. And this is kind of the great thing about QC problems. I don't really care what these numbers are. All I care about is this one's going to be bigger. I've got more 2's over here, so it has to be bigger. So part of the idea here is, remember I said simplify and pick numbers to try to prove D. But another idea we could have in mind is that our goal is to compare, not calculate. And part of what these simplification techniques can let us do is compare without calculating. So let's try another in that vein. Okay, so here we've got a sort of gnarly looking fractions and percents problem. And the first thing I'll say here is, if you didn't already know this, that word of means multiply. So one way to do this would, of course, be to just actually solve this out. Do 0.012 times 4 divided by 500 times 0.01 times 150. But before I do that, I'm going to notice here there's so much similar between these sides. So how can I simplify it before making those calculations? Well, the first thing I might do is just get rid of these 150s. Then it might be helpful to try to get everything in one form. So I'm going to make everything here a fraction. Call this 12 over 1,000 times 4 over 500 times 1 over 100 versus 12 over 10,000 times 4 over 50 times 1 over 1,000, which is 0.1 over 100. Okay, now maybe I'm going to simplify things a little bit more and make them all one fraction. So 12 times 4 times 1 over 1,000 times 500 times 100 versus 12 times 4 times 1 over 10,000 times 50 times 1,000. So already it's looking, I've just rewritten it in a way that I can see some of these relationships better. And maybe from that, I can just say, all right, I don't need to care about these 12s and 4s, right? Really what I'm doing is dividing both sides by 12 and by 4. And then here, maybe I realize, so I've got 1 in my numerator for both of these. In my denominator, I'm just going to have 5 times this number of zeros. So 5 and then 1, 2, 3, 4, 5, 6, 7. Let me put some commas in there so that it looks a little clearer. So it's 50 million versus here I've got my 5, and then let's count the zeros. 1, 2, 3, 4, 5, 6, 7, 8. All right. So here I'm dividing by a bigger number, which means quantity A is bigger. Now you may look at this and say, that was more work than actually just multiplying it out, and that may be the case. I'm not saying this is the best way to do this particular problem, and in this particular problem, there's like a million different ways we could simplify it and could use the similarities between the two sides to make a comparison. But I'm showing you a rather extreme way of doing it, just as another way to show you that we can simplify to be able to make a comparison. So we're trying to set it up in forms that they can be compared. We're trying to get rid of things that are the same and then be able to compare our sides. Let's try another problem. Okay, so we have here another problem where solving it out might actually be pretty difficult. So this is going to rely a little bit on some exponent rules, but I'll try to be clear about it and I'll open up for questions. If there's anything that I do that you don't follow, please let me know. So before I go and calculate things, I want to first just say, do I see any common terms? Well, I've got 4 squared and 4 squared. So I'm going to multiply both sides by 4 squared. It's technically what I'm doing, but I can eliminate those. 3 squared and 3 squared, same thing. From here, things get a little bit more complicated, but 2 squared and 2 to the 4th. If I divide both sides by 2 squared, using my exponent rules, I here get 2 squared. And that rule is that like x to the 3rd divided by x squared is equal to x to the 3 minus 2. You subtract your exponents if the base is the same. That's what I'm doing here. The next thing I would do is I would rewrite these 45s as 4 times 9, or 4 times 3 times 3. Oh, sorry, not 4, 5, excuse me, 5 times 9. So 5 times 3 times 3, and 5 times 3 times 3. This is pretty nice for me because I see I've got 5 squared and I've got 2 5s. Boom. I see I've got a 3. Let me get rid of one of these 3s. So now what I'm left with here is 75 times 2 squared over 3 to the 3rd versus 10. And just looking at this, my intuition says this side is bigger, but I could also work that out. Now, one way I could work that out, rewrite 75 as 25 times 3, and then eliminate one of those 3s. So 25 times 2 squared divided by 3, which is 100 over 3, which is about 33.3 repeating, versus 10, that's going to be bigger. So when you're doing a problem like this on the test, again, you don't have to go as far as I did. I'm partly doing this just to show you how much simplification might be possible in a problem like this. But you do want to say, can I at least do these simple steps, right? Can I get rid of the 4 squared and the 3 squared on both sides, even if you don't do anything else, just to make your life a little bit easier with your calculations? Be prepared to do that kind of simplification. Now, again, here I was relying on knowledge of some exponent rules and factoring as a technique. Maybe you're not there yet. That's totally okay. If that felt difficult, first of all, please send me your questions about any of the steps here. But secondly, also just keep in mind, like, okay, as I learn more of these rules, as I get more comfortable, know that I can do this kind of simplification. Take a moment to take questions. Okay. So far, all the ones we've been doing have only dealt with numbers. I want to now start introducing variables into this. Send me your answer to this when you have it. Okay. So as a general rule, it's often helpful to try to clear out our denominators. And in this case, that denominator is the same on both sides. So I'm definitely going to start by multiplying both sides by 82. To cancel those out. And this is a case now, 2a squared minus 4 versus 8a squared, where I could plug in, but I think it's definitely better to try to group your a squareds. So I get negative 4 versus 6a squared. And at this point, I would say we actually know the answer is B without even plugging anything in. Give you a second to think about why. It's because this side is negative. And I know anything squared has to be, x squared has to be greater than or equal to 0. So the smallest this could be would be if a is equal to 0. If a were a negative number, squaring it makes it positive. So b has to be bigger than negative 4. So in this case, I don't even need to plug in numbers. Maybe I do. If I don't see that rule, I plug in and I see I keep getting b. If I do see the rule, great. Let's try another. So you're going to start getting a little bit more complicated. Okay. So this is a case where we want to gather our like terms. So let's get our q's together by adding q to both sides. Gives me 5q minus 5 versus 10. And I'm going to add 5 to both sides. Get 5q versus 15. Divide both sides by 5. Get q versus 3. And at this point, I want to refer back to my upfront info. Well, simple enough. I know Q is less than 3. So my answer is B. Now, at this point, we've started using variables. The question I have is, how does that change things? So here's an example problem that's going to hopefully reveal something about how we work with variables when we're doing this hidden inequality trick. Take a stab at this and send me your answer. Okay, so it may be very tempting here. I see I've got x on both sides. To divide both sides by x. That would give us 4 and 5, which makes it seem like b is bigger. But that's not right. So let's look at why. Well, another way I could do it, instead of dividing by x, maybe I subtract 4x from both sides. In which case I get 0 and x. And I know x is less than 0. So the answer is actually A. And if I went back up here and plugged in numbers, I could see that, right? If I said, all right, x equals -1, I would get -4 and -5. If I try to fraction, I'd get -2 and -2.5, still getting A. No matter what I tried, if I tried an extreme, staying with this, an extreme, -40, -50, I still get A. So A is my actual right answer. So the question is, what went wrong over here? This comes back to what I was saying before about how when we're doing these, we don't multiply or divide by negative numbers or by variables that could be negative. So in this case, I'm told explicitly that x is negative. So I really want to avoid multiplying or dividing for exactly this reason. It gives me the wrong answer. Subtracting, adding, always good. Multiplying or dividing, no good. Now, I want to focus on this idea of that it could be negative. So let's change this problem just a little bit. If we got rid of that, I could still run into the same problem, where if I divide by x, I get 4 and 5. B looks like my answer. But I know that's not correct, because I could plug in x equals 1 or x equals -1. So my actual answer here is D. And when I divided by x, I messed that up. So pay attention to, is your variable defined as negative? Is it undefined? Or is it defined as positive? If it's like this, great, divide by x all you want. So if we had a problem like this and they told us b is greater than 0, cool, I can start by multiplying both sides by b, solve it out from there. But if they tell me b is negative, or I don't know anything about b, I need to pick numbers. So let's try one last one, and then we'll open up for questions. Okay, I'll stop you there. So the first thing I'm going to notice here is x is positive. That's good because I've got x in the denominator here. So I know I want to get rid of it. So I'm going to multiply both sides in such a way that I can get rid of all my denominators. I'm going to multiply both sides by 4x. So here, what that's going to do, those x's will cancel, and that 4 will cancel into a 2. So I'm just going to multiply all of these by 2. 8x squared plus 4x squared plus 6x plus 9, plus 18, excuse me. And then I'm going to combine these x squared, so 12x squared plus 6x plus 18. Over here, this gets multiplied by 4x, so it's 8x squared, next one by 4x, 4x squared, next one by 2x. So 6x plus 18. Let me combine my x squareds. And I'm just going to put a space there so we can see this a little more clearly. That in fact, these are the same. So my answer here is C. And I get there without plugging in any numbers. So could I have started out plugging in numbers? Of course. But it's pretty easy to make an arithmetic error somewhere such that you end up not getting C as your answer. Okay. Questions on this problem? Okay. So at this point, I want to thank you for a wonderful session. I hope this was helpful. I know we're like sort of in the weeds with a problem type that maybe you feel like is like a little advanced. If so, that's okay. If you felt like you were able to follow it, great. I hope this was helpful regardless. Again, I want to remind you all, check out the other recordings, the backlog of these going over everything, quant and verbal, all sorts of different stuff. At this point, I'm going to stop the recording